At birth, the human brain occupies roughly a quarter of its adult volume. By age 3, that scale doubles. During these first 1,000 days, the central nervous system exists in a state of hyperplasticity. The structural architecture of the mind is highly malleable, behaving like wet clay. This malleability is driven by synaptogenesis. Every second, a healthy infant generates 1 million new neural connections. We generally treat the baby's first smile or their first unassisted step as sentimental memories captured to share with family. Clinically, these behaviors provide rigorous, observable data, confirming that the central nervous system is maturing correctly. Understanding this biological system requires mapping the optimal timeline of development, identifying the systemic failures that trigger diagnostic alarms, and examining how modern environmental inputs shape pediatric neurobiology. These milestones provide a real-time assessment of the structural integrity within the developing neural network. The brain wires itself through interaction. Every sound, touch, and sight acts as an external stimulus that forces biological neurons to link together and form permanent structural pathways. Consistent auditory input creates distinct structural advantages. Reading aloud to a 3-month-old infant, even before they comprehend language, correlates with a vocabulary 60 times larger by age 3. Physicians rely on a specific sequence of physical actions to verify that this hidden neural construction is on track. By 2 months, the visual cortex and facial recognition centers mature enough for the infant to produce a social smile and identify their mother's face. Between 5 and 8 months, the core muscles and spatial awareness synchronize, allowing an infant to roll over and eventually sit completely unsupported. By 10 months, the motor cortex manages the complex cross-body coordination required for crawling. By 15 months, this processing evolves into independent walking. Cognitive complexity scales alongside mobility. Between 18 and 24 months, a child demonstrates targeted pointing and begins forming 2 to 3-word sentences. Hitting this sequence of physical benchmarks proves that an infant's sensory processing and motor cortex are evolving in biological synchronization. The timeline we just mapped represents statistical averages, but pediatricians also track the absolute outer boundaries of these windows, known as upper limits. Crossing an upper limit without achieving the corresponding milestone is categorized as a clinical red flag, requiring immediate medical evaluation. Stable neck holding usually develops within 3 to 5 months. If a child still cannot support their own head by month 6, it indicates a failure in the system. In later stages, failing to stand with support by 12 months or failing to walk by 18 months triggers identical diagnostic alarms. These specific motor deficits frequently trace back to perinatal neurological trauma sustained during birth. When a baby fails to cry, they fail to breathe. This birth asphyxia cuts oxygen, degrading fragile neural tissue. This starvation leads to hypoxic ischemic encephalopathy, creating physical lesions within the motor cortex that interrupt pathways needed for standing and walking. Crossing an upper limit serves as a diagnostic alarm, signaling underlying CNS damage that requires immediate physical intervention. Non-motor deficits are also rising. In India, current clinical data shows that 1 in 64 children is suffering from autism spectrum disorder. Autism operates as a neurobehavioral condition defined by social communication deficits, distinct from physiological infections like pneumonia. Diagnostic screening for toddlers over 18 months focuses on behavioral absences, a lack of eye contact, failing to respond to their own name, and the inability to point. The condition also presents through restrictive, repetitive behaviors, such as spinning the wheels of a toy car for extended periods instead of engaging in imaginative play. Identifying root causes requires separating a child's biological predisposition from their exposure to external environmental factors. Environmental variables, from food additives to pesticides, act as catalysts, triggering latent genetic symptoms into behavioral disorders. We now observe virtual autism. Hours of daily smartphone use chemically induces identical behavioral symptoms in toddlers with 0 genetic predisposition. By exposing the hyperplastic pediatric brain to excessive digital stimuli, modern environments contribute to the rise of neurobehavioral dysfunctions. During a tantrum, a toddler's emotional center, the amygdala, runs hot, while the prefrontal cortex remains immature. Scrolling short-form videos hijacks this state. Rapid visual inputs flood the brain with dopamine loops, bypassing the prefrontal cortex and overstimulating the amygdala. This dopamine saturation raises the child's baseline for stimulation. Once the screen is removed, the pace of normal reality feels intolerably slow, leaving the child agitated and emotionally dysregulated. The physiological damage extends into sleep cycles. Concentrated blue light emitted by digital displays suppresses the brain's ability to produce melatonin. Melatonin suppression prevents entering deep sleep. Only during these restorative cycles does the pituitary gland release the human growth hormone required for physical development. Because of these impacts, clinical guidelines dictate zero screen exposure before age 2. For children aged 2 to 5, exposure is restricted to 1 hour of interactive co-viewing. Screen time must be separated from meals. Watching a phone while eating creates a robotic intake pattern, interrupting the infant's ability to develop sensory associations with the texture and taste of food. Toddlers given screens receive a chemical intervention that interrupts growth hormone cycles and shifts the foundation of their emotional development. The first 1,000 days of human life represent a phase where intelligence and emotional regulation emerge as structural outcomes built by physical interaction. These cognitive traits are constructed neuron by neuron through continuous sensory inputs. Treating digital technology as a convenient pacifier introduces a neurological disruptor directly into this vulnerable building process. Monitoring developmental milestones provides time-sensitive medical diagnostics regarding the integrity of the neural network. Ultimately, the parental role during this hyperplastic window directly constitutes the engineering of a human central nervous system.